Okay, so let us continue from where we left in the previous video. So, we had actually done earlier the lemma 1 and lemma 2, which in fact defined that what happens in a delta network. In general, that also happens in a Banyan network. So, the assumptions which we are going to make in a delta network analysis, in fact we are more interested in doing buffered delta analysis. So, assumptions will be as follows. So, let me list down all assumptions. So, assumption number 1 will be that, which of course is obvious, but I am explicitly writing it, that each packet arriving at the network, so at the inputs actually, will has data, and of course I am also assuming it also has a label which will decide to which network output it has to go. So, it is a label identifier. So, mostly when the packet comes at the input, there is a processor board which will actually insert a tag or a label which will be used for self routing inside the switching network. So, we define this as well as a label. Of network output to which packet is to be transferred. Okay, so that is the first assumption. We are also going to, when we are doing this analysis, we will be talking about condition of maximum loading. Okay. So, this will simplify, in fact we do actually can use it, but we are interested in what is the maximum loading condition and we want to compute for that. Condition of maximum loading exists. What does it mean is that at the network input links at the switch. So, when I talk about a switch, so there are multiple switching elements in a buffer in the switch, multiple switching elements in a stage, and they are being interconnected. Okay. So, each one of these are also going to have a buffered thing in a buffered delta system. Every switch input, every switching element input will have a buffer. What I am saying is that these inputs will always have, these switch inputs will always have a packet available. The moment you push a packet out to the next stage, immediately the packet will be coming into the input. There will not be any instance when packet is not available. So, that is a maximum loading condition. Okay. So, probability that a packet is going to be there in a slot is equal to 1 here. Condition of course, if the packet moves out, moves further. If packet cannot be moved further, then the earlier packet will remain there. Okay. So, that is a condition of maximum loading. So, which actually implies there is a single buffer at the network input link So, which implies this. So, there is a buffer here. So, which in fact is a buffer is a part of the switch. Filled by an input packet whenever buffer is emptied. By the network. Okay, so that is the second condition, which assumption which we are going to make. And of course, now what happens to the outgoing links? Whenever the packet is going to be reaching at the outgoing link it is going to be immediately emptied. Okay. So, we need to state that also as part of the second condition. So, let me continue here. Okay. So, the second one continues and it says buffers at the network output links are emptied instantaneously. So, there is no waiting. Okay. In fact, I should write instantaneously, that is assumption. Instantaneously. Okay. The third assumption which goes is I call it a uniform loading condition. All input packets independently and equiprobably directed to each network output link. So, this implies whenever the packets are coming in, irrespective of which is the input, they will be actually all will be independent of each other, and with equal probability they can be directed to any one of the outgoing port. So, you take any input output pair, they will actually have the same amount of traffic. So, that is what actually this is the independent and equal probability distribution. We call it in common terms uniform loading condition. Okay. So, the fourth assumption which we are going to make here for this analysis model is delay at every 2 by 2, we are taking 2 by 2 crossbars at 2 by 2 switching elements. Consists of 2 time intervals So, this is required so that I can do recursive I can do iterative computation. So, depending on we call it these 2 time intervals will be known as, one of them is known as Tpass. This is a time which is required. So, if a packet is lying here in this buffer, it has to be transferred here. So, there is a line rate at which the packet can be transferred on to this side. So, if it consists of 1000 bits, so whatever is the line rate, I divide by that 1000 bytes divided by number of the bytes per second at which you will transfer, that will give me the time in which the whole packet will be moved out to the next stage. So, that transmission rate will define the Tpass. Okay, so, this is the time taken, time needed to pass the data to selected output. So, this one fragment Second fragment, second one will be what we call TSelect. So, what happens when two packets are going to come here? There is a local processor inside the switching element which will analyze the tags or the labels and will identify which packet has to go to which outgoing port. Now, this decision making time is what we know as TSelect. So, first of all, when the packets are there, there will be TSelect, it will be decided which packet will go to which output or whether it will not go, it has to be kept in the buffer, and then that TSelect phase will be over and then Tpass will start. Okay. So, this is that particular time. TSelect is the time needed to select a switch output. Okay. So, in fact, the minimum delay which will be incurred. So, in first stage it will actually take TSelect plus Tpass, and if there are n such stages, so total time in which a packet will move from input to output link, in the best case when it is not going to be buffered in step by step, it is going to move. So, the minimum delay which it will incur, I call it Mindy. So, this should be n into TSelect plus Tpass. So, we define this as a Mindy. Okay. So, this will be required as a benchmarking because there is a minimum delay. So, on an average whatever is the delay which is being suffered by a packet because of buffering, we divide by this and we get a normalized delay actually in that case. So, when there is no buffering, then what is going to happen? So, when there is no buffering, the packet cannot be buffered, packet has to come and it has to be routed all through in one single stage. So, in fact, the selection will be done here itself at the input of all the packets, all the stages, all of them will be connected in one single go, and then the packet will be transferred all the way from input to output in one single shot. So, only delay which will be suffered by a unbuffered system will be Mindy. Okay. So, that actually means now that is one case when we do actually the single processor has to set up everything. Okay. This case that not Mindy, but that in that case will be TSelect plus Tpass. So, that is like everything is being controlled by one single processor, headers are being analyzed, everything is being switched and then routed. So, TSelect will be required here and Tpass in one single go going through, which is going to be also true for a single crossbar system. But if you have this kind of system and there is no buffering, so a packet comes here, it is being selected, passed out, packet analyzed, passed out, packet analyzed, passed out. If there is a conflict, packet is simply dropped. In that case, unbuffered system, the packet will be requiring TSelect into n Mindy amount of time for reaching from input to output. So, unbuffered system, the minimum delay will be Mindy. In fact, the only delay will be Mindy or infinite, either packet will be delivered or it will not be delivered. Okay. So, but in case of a buffered system, packets can get buffered. So, it will not be between two choices of either Mindy or infinite, it can be somewhere intermediate also. Okay. So, when the network is going to be with buffers, what you are going to do? So, the fifth thing, let me write it down. So, that is whatever I have stated. So, fifth assumption is about this for unbuffered delta. for network without buffering, output data is delivered in Mindy. So, switch will be attempting to transfer the packets, input packets to a corresponding output through a unique path, okay. And if there is a clash, some of them will be actually dropped, only one of them will be going to an outgoing port, the remaining will be dropped, okay. So, there is no priority, any one of them, if there is a two packets are contending at a 2 by 2 crossbar in intermediate stage, one of them will be with equal probability will be dropped actually. So, that is with buffering, without buffering. So, sixth one, what happens with the buffering actually. So, here I have to give you the Patrinet model, which is technically can represent a 2 by 2 element with buffering. Now, remember I am going to do back pressure mechanism is going to be implemented when the network is with buffering. If buffer is occupied here, then the packet cannot move from this to this, it is not possible, this will also remain buffered. Only it is possible if this packet gets emptied, then the next packet can go in, okay. So, this is for network with buffering. So, if this is can be modeled as a Patrinet, so it is a timed Patrinet actually. So, Patrinet is basically used for finite state machine modeling. So, what does it actually means in general? Let me just explain what the Patrinet is and then I can draw the model. So, here the idea is if we actually have something called token buffers. So, these tokens will be there and whenever a token is present I can trigger an event, okay. And when both tokens are present in both the preconditions, the event will be triggered and this can lead to tokens into one of these, or there can be another condition. So, when these two tokens are consumed I can actually generate two more tokens, I can generate any one of them depending on the condition which is specified on this decision threshold. I can also put a timer. So, if these two are available, after that it will take some time t, after which only this firing will happen, these tokens will be consumed and new tokens will get generated, okay. So, essentially the idea is this thresholding mechanism or decision thresholding and the this token holding buffers and token holding buffers on the outgoing side. So, using basically this element we can actually create a model for a 2 by 2 crossbar. So, let us do for 2 by 2 crossbar which is buffered system, that is what we are using. So, we actually will have an input buffer. So, packet can be hold there. So, this is the from one side. Now, I am also going to inform to the previous switch whether I have the buffer is empty or not empty. So, we call it a buffer empty flag, okay. And there will be another buffer empty flag because the 2 by 2, so this is the input 1. So, to whichever actually previous stage output it is connected, this buffer empty flag will be giving a signal there and the packet when it is will be transferred, this input buffer flag will also get occupied, okay. So, we will have another one which is going on this side and then there is an input buffer, okay. Not here, sorry. Now, whenever the packet is there, in these two, then I can come to a decision. So, this decision actually takes time TSelect. So, this is the TSelect which we have defined earlier in the assumption. If packet is available, it will take some time TSelect before it can make a decision that I need to move the packet to the outgoing buffer. Okay. So, if this happens, then I will have what we call output request flags. So, if there are two packets which are trying to contend to the same outgoing port, so there is outgoing port 1 and outgoing port 2, then they will contend and one of them will be selected within time TSelect and they will end up in. So, if this one is being selected, then this will be emptied and this will be occupied and this will remain as it is, so that it can be transmitted in the next time slot, and if this is selected, this is not, this will be triggered and this will get occupied, this will be emptied, this remains as it is. Okay. So, similarly we will have on this side so because this packet can go on to also this side also, and I will have another output request flag which will go in this fashion. So, one of the two, oh sorry, I think I will be keeping two of them. Okay. So, only one of them will get selected, it will come here, and then we will have the packet whichever will be selected for passing out. So, this token comes in and there is a precondition that there is a successor, the next switch, from there we will have a successor buffer empty flag. This is basically this buffer empty flag of the next switch. So, this has to come and this has to now get. So, I am putting it a dashed line because it belongs to the next one, but it is connected here. So, if the buffer is empty, output request flag is on. So, whichever one gets selected, one of them will be selected at any point of time. So, either this gets occupied or this gets occupied or this or this. So, one of the two always will be occupied, not both of them. So, and the buffer empty flag is also there. In that case, triggering will happen and it will cause the packet to actually move to the next buffer. So, in that case, this is what we call input buffer will be there, which will get triggered. So, packet will be passed on to the next buffer and this buffer empty flag has to be triggered. So, I will now create a link from this place. Okay. So, the next now switch will be knowing that he can push in the packet here. Okay. Now, this will actually take time called Tpass. So, in this time the packet will be moving out from the previous buffer to the next buffer. Okay. So, same is going to happen here. And of course, if this particular thing is selected and this gets triggered because this buffer was empty, in that case actually from the lower buffer the packet transfer will be happening. So, this buffer empty flag has to be triggered. Okay. So, similar logic applies on the bottom side, and I will have again whichever is this can be for a different switch, this can be for a different switch, remember. These two are these all four may not be belonging to the same switch. Okay. So, this goes in this fashion this is also successor, buffer empty flag, and this is successor input buffer. This is also successor input buffer. Okay. So, in fact, no, I should keep it dashed because this belongs to the next one. And if this one is selected, so this input flag goes, this one is selected, then this input flag goes. So, this is what will be the patternate model for the 2 by 2 crossbars which we are using for a buffered system. Okay. And remember that there is a back pressure mechanism being maintained by these buffer empty flags. So, unless a buffer is empty, you cannot actually move a packet from the previous stage to the current stage. So, as the packets are being delivered at the output port side, there is going to be a reverse flow of this empty flags, and the more packets from the input side can be pushed into the system. So, what we will be doing is, for analysis purpose, we will be now analyzing everything in terms of. So, these are the assumptions which we will make. For analysis, the performance criterion will be throughput and of course, the turnaround time. Okay. And we can also create the normalized versions of these. So, turnaround time throughput will be the average number of packets going out per unit time. And turnaround time will be average time interval between instant when packet was placed an input buffer, input link buffer actually, and the instant when packet is placed in buffer at output link. Okay. So, if there is multiple stages, so how many packets at the output port are going out per unit time per port, that will be the throughput. Total switch throughput you essentially find out total number of packets going out per unit time for the whole switch. Turnaround time is the actually delay, average delay from input to output, that is what it means. And we can create the normalized versions. For normalized versions, the upper one will be divided by the maximum throughput which is possible. So, you divide by maximum throughput. So, you get a normalized version. For the turnaround time, you will find out what is the minimum turnaround time which is possible. You divide by that, so which is Mindy actually, and then that will give you the normalized versions of these two metrics. So now what we can do is, for doing further analysis, I can actually take two assumptions, and under two assumptions, each one of these assumptions I can do the analysis. So let us do that. So one of the assumption is that, in fact, there is a choice about what I do about the TSelect and Tpass. So there is a possibility I can assume that TSelect is 0, and then complete slot period is being going for the passing out the packet. Packet does not go in one go itself. Second thing is, packet the whole time is required for doing the selection. The packet can be transferred almost instantaneously. So infinite bit rate is there in the internal network. So Tpass can be 0. So or, so one of these two can be taken, and henceforth we will have two models through which we can do the computation. So T delay will now be given as, so that is a 1 slot delay, and of course we will assume at time t is equal to 0 there is no packet in the system, and at every t delay I am going to put the packet at the input buffers, if those buffers are going to get emptied. If they are not emptied, then I will just simply push them. So before we come on to this particular model, let me just quickly go through certain prerequisites which will give me better understanding when we will do the modeling. So this I will do in form of a lemma, and is proof which is obvious of course. So you have to just remember what were these assumptions, and from there we can derive them. So the lemma actually goes, so since the second lemma you can call it lemma 2, but now this is for a unbuffered system. So I think I should do it before we move to the buffered stuff. For 2 raised power n by 2 raised power n unbuffered system, and with of course all the assumptions which have been taken, we can define Pk as probability of packet passing through an input link in stage Sk. So here this actually goes from 0th stage to, because I am counting from 0, so it has to be n, so I am not making equal to, it is less than n, and this will happen in a Mindy slot. Okay. So this I have explained why Mindy slots will be required, because at every intermediate stage in a delta system there is a the packet has to be held for a small time and then transferred immediately. So in fact there is technically no buffering. If there is a conflict, you simply drop the packet, let the earlier packets keep on coming in. Okay, that is a buffered system, and Pn be the probability of packet arriving at an output link. Okay. Now important thing, that Pk for 0 less than k less than n, same for all input links in same stage. So, what does it mean if I have lot of switches? So, I estimate some pk here. So, this will remain same and this will be same for all links which are all input links, all of them which are there to this particular stage. So, pk will remain same irrespective of which link I choose. Okay. And similarly, Pn will be same for when you look at the outgoing link in the outgoing stage. So, Pn whatever you measure, take any one of these output links, Pn will remain same there. Okay. So, Pk is same for input links in the same stage, Pn is going to be same for all network output links. Second, what is going to happen is arrival of packets at an input link of a switch is independent So, arrival of packets at an input link of a switch is independent of arrival of packets at any other input link. So, what does actually interpretation is, if there is a switch, there are many input links which can be there. So, the arrival of a packet on this is independent of arrival of packet on this, these are independent of arrival of packet on this. So, all these input will behave independently, there is no correlation between the packet arrivals. Okay. And of course, for any delta network, it is not a set for certain specific one, Pk for 0 less than k less than n is same for all delta networks. All delta networks of size 2 raised power n by 2 raised power n. So, for size is same, whatever be the interconnection pattern, the Pk value will remain same. So, whatever is the result is true for all kind of delta networks. So, the proof actually is going to be very simple in this case, this can be done. So, I am not doing it formally here, but I am stating how this actually can be done. You do it by induction. So, you prove it for 0 and henceforth prove for k is equal to 1. Okay. And once if it is true for 0, it is true for 1. You just prove if it is true for k, it is going to be true for k plus 1. So, henceforth by induction it is actually true for all values of k. So, that is the way it is going to be done, induction of k, where k will go from 0 to n. So, you will actually use this. So, a statement is true for stage 0 because of assumptions 2, 3 and 5. For stage 0 it is true because of the assumptions which we have I had written earlier 2, 3, 5, and for stage k, if it is true for stage k, it is going to be true for k plus 1 this will come from the assumptions theorem 1 and assumption 3. So, theorem 1 which we have done earlier and assumption 3. So, once you do it, this actually can be proven, and of course, from there you can compute we can actually build up a theorem. This in fact is the same result which we have done earlier. So, we can identify a theorem from here, and this for all delta networks actually. So, since the second one I am talking about, you can call it theorem 2. So, it says that all 2 raised power n by 2 raised power n. Now, this is for unbuffered deltas. With all the conditions which we have assumed. Will have same throughput. So, this actually throughput will turn out to be nothing but P of n, total number of outgoing ports is this, and these packets goes out in Mindy slot. Okay. So, throughput is going to be same because Pn is same for all kind of switches. Okay. It is as simple as that. In fact, we have done this analysis earlier, and the result was that I can always estimate through recursion. I can get Pk plus 1 will be coming as 1 minus Pk by B raised power B. Okay. So, this B is in our case will be 2 because a 2 by 2 network. Okay. And P0 will be 1. We are using the maximum loading condition, and henceforth we can compute whatever is the value of Pn, and we can put the value and compute the throughput. Okay. And of course, the normalized throughput will be whatever is the maximum possible throughput. So, when Pn is 1, there is the max 2 raised power n by Mindy is the maximum throughput. So, Pn will become the normalized throughput. Okay. So, this is a normalized throughput which will be there, and of course, using similar formula we had earlier done something for a crossbar, and for the maximum loading condition when P0 is 1, our throughput was 0.632, which we have already computed. Okay. So, now let us move to the buffer delta system analysis. Now, as I was mentioning that packets will be put into the system input at every t delay. So, at every instant tk, which is going to be k times t delay, packets will be put in. So, k can take a value from 0, 1, 2, 3 and so on till infinity when the switch is operating, and we actually can build up with a single buffer in for every intermediate switch. I can actually build up a Markov chain and do the analysis with that. Okay. But that will be very cumbersome because you will have almost a large number of states which can be there in the switch operation. So, we will not do that. We will actually use an alternative trick. We will try to use minimum number of state for each switch, and then we will iterate. We are actually going to use the assumptions that all switches in any stage are almost same, almost similar. So, let us take with first condition we will take is when Tpass is 0. So, packets can be transferred almost instantaneously, but before we move, I need to tell you that what is the difference between Tpass and TSelect, what is the consequence of that, so that you can appreciate. So, when Tpass is 0, typically a switch will be having some connection like this. Let me show you what happens. So, let these two packets which are there have to go here. So, this has happened at some instant in some time slots, each one of them is equal to T delay. Now, Tpass is 0, it actually means TSelect is equal to T delay. And each slot is equal to T delay. So, selection process itself actually takes complete full slot and packets are transferred instantaneously. So, when both packets actually arrive here, it will take this whole period for the selection to happen. And then the next buffer which is available here for this switch, only one of the packet can be pushed out almost instantaneously at this point. But the packet has to be held up here because again it has to go through a T selection process. So, what will happen in the next step is, let me draw it above this. So, once we move here, so only one packet will be able to move to this outgoing packet, this buffer, and this will be the situation now. And then the next complete slot will be required for again doing the selection process. By that time new packet actually can come in, will not be able to come because this buffer was not empty. Now, this buffer is not empty, so this signal will not be coming back. Remember what we have built as a Petri net model. Unless this buffer is empty, there is no use of doing any selection here. This buffer has to get emptied first. So, there will not be any selection for this outgoing port in this time slot. This buffer is free, so this will get selected, and assuming that there is no contention from the bottom one, there is no contention here, this either might be going to this second port or this is packet itself is not there, one of the two conditions. If there is going to be contention, then of course one of them will be going out. So, assuming this is going to go on to this side. So, at the end of this next slot, this will not be selected because buffer was not empty, this can get selected, and then will be at this instant this packet can move to the next location. So, you will have this situation. Now, in the third time slot, the selection will be again happening here as well as here as well as here. So, this buffer is empty, so selection will take place in this time slot. For this, the buffer is immediately being emptied out at the output port. So, this will be also selected in this same time slot. At the end of this position, these will be actually now moving on to this place. So, there has to be a one buffer which has to be empty here, then only this thing can happen. So, this is the consequence when I am going to use Tpass is equal to 0. When I am going to use TSelect is equal to 0, then how this same figure will look like. So, let us put TSelect is equal to 0. Oh, I think I have made a mistake. We need not actually have, let me just repeat it. When TSelect is Tpass is 0, what I have done is for TSelect is equal to 0. So, unless the buffer is emptied, you cannot push the packet out. So, but when Tpass is 0, packet can move almost instantaneously. So, we do not worry about the buffer being emptied or not. So, when these two are there, this is empty. So, in the next time slot, you will actually have a packet moving on to this side, one packet here. In the next time slot, both of them can get selected. So, this gets selected to move here, this gets selected to move here. In the next time slot, this is what is going to happen. So, they can synchronously keep on moving further. But when we have TSelect is equal to 0, then this will not be happening, because one of the packets gets selected, it is here, second one is here. Now you cannot move this packet onto this side till this actually packet becomes empty in the next slot. So in the next slot this packet will be transferred, then this will get emptied, and next to next slot this packet can move. So this packet will be, there will be intermediate stage when this goes to this location, and the next time both of them will be moving simultaneously. So that is what will happen with TSelect is equal to 0. So now in order to actually simplify, we need okay, we will actually continue with the next stuff in the next video, where we will discuss how we will be actually moving from, we will be using, we will be creating this time and bifurcating into 3 separate events, so that we can easily now model this whole show, model this when t passes 0, how to model the computational procedure. When TSelect is 0, it is far more simpler, but for t passes equal to 0, I need to break up this into 3 separate consecutive events which has to happen at every switch.